Today we are going to discuss about the force on a current carrying conductor placed in a uniform magnetic field. So when a current carrying conductor is placed in magnetic field, what happens with it? Now suppose we take a conductor, it is carrying current I, and suppose this conductor is placed in some uniform magnetic field. Now what happens? Current carrying conductor means the charge is flowing through this conductor, and you know very well, when a charged particle moves in a magnetic field, let magnetic field is V, then a charged particle experiences a force F, and it is given as Q V cross B. This is the magnetic force working on a charged particle which is moving with the velocity V, and magnetic field is V. So this expression tells us the amount of force as well as its direction. Now as a conductor is carrying current, it means charge is flowing through this conductor, and we take the direction of current as the direction of flow of positive charge. Okay, now if we take this expression from here, we can write Q. Suppose this conductor, we are taking a length L of this conductor, L. Suppose this portion we are taking inside the magnetic field, so we are taking its length as L. So here this charge travels a distance L, let it travels in time T. Then this V can be taken as L upon T cross B. Okay, so in time T, charge travels a distance L here. If we take time outside, it can be written as Q upon T L cross B. But charge Q is flowing through this conductor in time T. Okay, so charge flowing per unit time through the conductor is known as current. So it can be written as I L cross B. This is force. So hence we can express the force experienced by a current carrying conductor placed in external magnetic field. So if length L is of the conductor inside magnetic field, then force will be I L cross V, and from this we can find its magnitude as well as direction. Direction of force can be found from this expression also. It is the cross product of L and B here multiplied with current I. So this cross product gives us the direction of force on this conductor. So in general, suppose we are taking magnetic field in one direction, and that conductor is, its current is along this direction, so L is also having this direction along the current. So if the angle between this vector L and magnetic field is theta, then force, magnitude of force will be I L B sine theta. And what about the direction? Here, according to cross product of vectors, the resultant vector F will be L cross V, means if we take our right hand and first of all we keep the fingers along the direction of vector L. Vector L means that along the direction of current, and we fold our fingers from the vector L towards vector B. Then thumb represents the direction of force on the conductor. So we can use this right hand palm rule, as well as we can use Fleming's left hand rule. What is Fleming's left hand rule? Fleming's left hand rule tells us that if we take our left hand and stretch our thumb, forefinger and central finger in mutually perpendicular directions, then if forefinger represents the direction of magnetic field and central finger represents the direction of current, then thumb will represent direction of force on the conductor. So here vector L is representing the direction of current. So if we take this example, here current is along this direction and magnetic field in that direction. If we take mutually perpendicular directions, suppose here, then magnetic field is perpendicular to the plane of paper, current is upward, then force on this conductor due to magnetic field will be in this direction. For magnitude of force, this expression can be written as F equals to ILB sine theta, where theta is the angle between magnetic field and current carrying conductor. In general, if we take a conductor and current flowing through the conductor is in this direction, I, and suppose magnetic field is along this direction, then angle between the direction of current means length of conductor and magnetic field is this theta. So force on this conductor due to magnetic field will be ILB sine theta or BIL sine theta. So it depends on the angle between them. But if these current and magnetic field are perpendicular to each other, like here as we have taken case, magnetic field is inward to the plane of board and current is in the plane of board. So here force will be maximum because theta is 90 degree, so it will be simply ILB or VIL. Now we will discuss the force between two parallel current carrying conductors that near each other. Here suppose we take two conductors, these are parallel to each other and both of these conductors are carrying current. Conductor 1 is carrying current I1 while the second conductor is carrying current I2. Here we have taken both the current in same direction in these parallel conductors. Now as we know that whenever a current carrying wire is there, around it a magnetic field develops. So magnetic field develops around the current carrying wire is given by this expression. Magnetic field due to an infinitely long current carrying wire, B is mu naught I upon 2 pi r. Means at a distance r from the conductor, if the conductor is carrying current I, magnetic field will be mu naught I upon 2 pi r. Now take the case here. Conductor 1 is an infinitely long conductor. It is carrying current I1. Now if we take a point here in the vicinity of, in the position of second conductor, let we take a point here. At this point is at a perpendicular distance r from conductor 1. So due to the current of conductor 1, there will be a magnetic field B here. And here we are representing this magnetic field as B1. B1 is magnetic field due to conductor 1, current I1. This magnetic field B1 will be mu naught I1 upon 2 pi r because current is I1 and distance is r. So this much magnetic field will be developed due to current I1. Now what will be the direction of magnetic field? The direction of magnetic field is known by right hand screw rule or right hand thumb rule. According to right hand thumb rule, if we place our thumb along the direction of current and fingers towards the point where we want to find the direction of magnetic field, then in whatever direction the fingers will fold, that represents the direction of magnetic field at that position. So here at this point, that because current in conductor 1 is upward, so thumb is in this direction, fingers are towards this point and they are folding inward to the plane of board. So that is why magnetic field B1 at the position of second conductor, at each point of second conductor, magnetic field will be inward. So it means this second conductor, which is carrying current I2, it is placed in a uniform magnetic field B1, because at each point the distance of second conductor is R. So this much field is there, uniform magnetic field B1. Now already we have studied that whenever a current carrying conductor placed in a uniform magnetic field, it experiences a force. So it means on this second conductor a force will be applied due to magnetic field B1, and that force on conductor 2 due to 1, that will be F equals to ILB sine theta. We have studied that. So I is current in second conductor I2. L, suppose we are taking L portion of the conductor from this whole length. For L length, force will be ILB. B is uniform magnetic field is B1 and sine theta. So here, because angle between magnetic field and current I2 is 90 degree, magnetic field is inward and current is upward. So both of these are making an angle 90 degrees. So it is I2LB1 sine 90 degrees. So this much force will be experienced by conductor 2 due to the current in conductor 1. And when we substitute for B1, so this expression comes out to be I2L mu naught I1 from here upon 2 pi r, and sine 90 is 1. So F21 is equal to mu naught I1 I2 into L upon 2 pi r. Or we can say that force per unit length of this second conductor, force experienced by unit length of second conductor due to the current in conductor 1, that will be mu naught I1 I2 upon 2 pi r. And what will be the direction of this force? Because magnetic field B1 is inward, current in conductor is upward. So if we take right hand palm rule, from that we can find L is in upward direction, magnetic field inward. So thumb represents the direction of force on this conductor. So it means a force F will be applied, F21 will be applied towards the conductor 1. Similarly, we can find the force on conductor 1 due to current in conductor 2. Similarly, we can find. Now, for that, what should be done? Firstly, we take a point here in the position of second conductor. First conductor, here we take a point, and current is in second conductor. Now, due to this current, a magnetic field will be developed across conductor 2, and according to right hand thumb rule, current in second conductor is in upward direction, and this point in the position of first conductor is in this direction. So we take fingers towards the first conductor from second, and our fingers are folding in outward direction. So it means a magnetic field B2 will be developed, that will be outward due to the current in second conductor I2. So B2 field will be outward. At each point of first conductor, same magnetic field B2 will be applied. Okay, so it means this first conductor carrying current I1 is placed in a uniform magnetic field V2. For that, we can find expression for force on first conductor due to the current in second conductor. Now, we will find expression for force on first conductor due to the current in second conductor. Now, due to the current I2 at a distance r from the second conductor, magnetic field V2 can be written as mu naught I2 upon 2 pi r. Similarly, as we have written earlier for B1, so here this current is I2 in second conductor, magnetic field due to current I2 is V2. So, in this magnetic field, this conductor first is carrying a current I1. So, this V2 magnetic field will apply a force on first conductor, and that force on first conductor due to 2 will be current in first conductor, ILB sin theta. I means current in first conductor, L length of conductor, and B2 in which field the conductor 1 is kept, B2 magnetic field, and sine of the angle between magnetic field and current. Here magnetic field is normally outward and current is in the plane of board. Okay, so when we substitute for B2 here, so it becomes I1L mu naught I2 upon 2 pi r. Okay, and again we get expression that force on conductor 1 due to the current in second conductor F12 is equal to mu naught I1 I2 into L upon 2 pi r. Or if we take force on per unit length of conductor 1 F12 upon L, so that will be F12 upon L. From here it is mu naught I1 I2 upon 2 pi r. So this time we are getting this expression, second one. So earlier we were getting expression for force on second conductor due to the current in first conductor. Okay, so we were getting force per unit length of second conductor, that was mu naught I1 I2 upon 2 pi r. Here also force on first conductor due to the current in second conductor F12 per unit length F12 upon L is mu naught I1 I2 upon 2 pi r. It means both of these conductors are expressing they are experiencing the equal force. But what will be the direction? Here for first conductor magnetic field is outward and current is upward. So if we take L cross B, then thumb represents the direction of force. So force on first conductor due to the second conductor will be here towards second one. So these two forces F12 and F21 are equal in magnitude but in opposite direction. So it means if currents are in same direction in parallel conductors, then these two conductors will attract each other. These are the expressions. And now if the currents are in opposite direction, then magnitude of forces will be the same but directions will be outward. Okay, that we can also discuss. Look at this case. Here in conductor 1, current is in upward direction, while second conductor, which is parallel to the first conductor, it is carrying a current in downward direction. So it means these two currents are in opposite direction. Okay, now what will be the amount of force? Here again current I1 is there, so at a distance r, magnetic field will be same V1, and because current is upward, so magnetic field in the position of second conductor, that will be inward. This is B1 and magnitude of B1 will be as before mu naught I1 upon 2 pi r. So due to this magnetic field, now in second conductor current is in downward direction, so force on second conductor due to the current in 1 will be I2L B1 sine 90 degree. Okay, so we get the same expression F21 per unit length, that mu naught I1 I2 upon 2 pi r. But what will be the direction here? Now, magnetic field is inward and current is in downward direction. So if we apply the L cross B formula, so length vector is along current I, so L cross B. So we are taking our fingers in downward direction according to the current, and magnetic field is inward, so for our right hand our fingers are turning inward. Okay, from L to B. Then thumb is representing the direction of force on second conductor. It means on second conductor a force F21 will be applied away from first conductor. Similarly, we can find the direction of force on first conductor. Due to current I2 at a distance r from second conductor, a magnetic field in the position of first conductor, current is in downward direction, and according to right hand thumb rule, we can find the magnetic field in position, because second conductor is carrying current outward downward, so magnetic field in the position of first conductor will be inward. So here this is the difference, that when currents are in opposite direction, here magnetic field B2 is also in inward direction. Okay, so magnetic field B2 is inward, current is upward, so according to L cross B vector product, then force on first conductor, which is placed in uniform magnetic field B2 throughout the length of conductor, then L cross B gives us the force on first conductor due to second one, that is F12 in this direction. So now these two forces F12 and F21, they are in opposite direction. They are equal in magnitude, they are in opposite direction, but these are outward. Means now when conductors carrying current in opposite directions, these two conductors, they repel each other. Now after discussing it, we will define 1 ampere current from these expressions. As we have found that force on conductor 2 due to the current in conductor 1 per unit length is mu naught I1 I2 upon 2 pi r. And similarly, the force on conductor 1 due to conductor 2 is same, mu naught I1 I2 upon 2 pi r. So it means these two forces are having same magnitude. F12 is equal to F21, and per unit length L, this is mu naught I1 I2 upon 2 pi r. Now from this expression we can define our 1 ampere. For it, suppose these two conductors both are carrying same current of 1 ampere. Means if I1 is equal to I2 is equal to 1 ampere, each conductor is carrying 1 ampere current, and let the separation between these two conductors is also 1 meter. They are separated by a unit distance, and unit current is flowing through each conductor. Now force per unit length of each conductor, that will be simply mu naught upon 2 pi, by substituting I1 and I2 as 1 and R also as 1 meter. So, and value of mu naught upon 2 pi is 2 into 10 raised to the power minus 7, and because it is force per unit length, so its unit is Newton per meter. Okay, so from here we can define 1 ampere. Okay, so 1 ampere is that current which flows in two parallel conductors separated by a unit distance, and if they apply a force of 2 into 10 raised to the power minus 7 Newton per unit length of each other, then that current is 1 ampere. Hence, we can define 1 ampere that if two parallel conductors, long conductors, kept 1 meter apart in vacuum, carry equal current and apply a force of 2 into 10 raised to the power minus 7 Newton per meter length of each other, then current in each conductor is said to be 1 ampere. Because as I have told you that here force per unit length of each conductor is mu naught I1 I2 upon 2 pi r. And if both conductors carrying equal current 1 ampere and separation between them r is 1 meter, so we get force per unit length as mu naught upon 2 pi, which is equal to 2 into 10 raised to the power minus 7 Newton per meter. So accordingly, definition of 1 ampere is given. If two parallel long conductors kept 1 meter apart in vacuum, carry equal currents and apply a force of 2 into 10 raised to the power minus 7 Newton per meter length of each other, then current in each conductor is said to be 1 ampere.